Scientists grow plants using electricity instead. If electricity were to take the place of sunlight in crop development, global agriculture may alter. The importance of sunlight to plant life is well known. The development of life on Earth has been fueled by the process of photosynthesis, which converts solar energy into food. But what if plants didn't require sunlight? Imagine if, instead of needing light, electricity could be used to grow food in complete darkness. An important departure from traditional agriculture is represented by the current research of electro-agricultural, or electro-ag. By supplying plants with acetate, which is produced by electrolyzing carbon dioxide, they have created a technique that totally circumvents photosynthesis. This strategy might revolutionize the agricultural output sector by allowing cultivation in previously unsuitable locations, conserving water and utilizing less area. The foundations of electro-agriculture. The idea of using energy to propel chemical reactions is not particularly new. Electrolysis, or the breakdown of molecules by an electric current, has been used since ancient times. But until lately, using it to feed plants was considered audacious. The efficiency of classical photosynthesis is quite low from an engineering perspective. Crops only convert around 1% of the sunlight they get into biomass. The electro-agriculture method developed by Zhao and his colleagues is theoretically 4 times more successful. Using electricity, carbon dioxide is first transformed into carbon monoxide, which is then transformed into acetate. Plants and fungi may use this acetate to make essential compounds like sugars and amino acids without even needing sunshine. The system is set up as a vertical farming concept, with electrolysis on the top floors being powered by solar panels on the roof. Crops develop under tight supervision in stacked growth chambers below, where they absorb acetate. To date, scientists have used this technique to successfully raise algae, yeast, and mushrooms. Other tiny crops, such as lettuce and tomatoes, have previously been tested. By altering common crops like wheat and sweet potatoes, scientists hope to enhance acetate digestion in the long run. We have demonstrated that solar-to-food processes are at least 4 times more energy efficient than photosynthesis. Large swaths of land might be made available for rewilding and carbon sequestration if electro-ag is completely implemented in the U.S., potentially reducing the amount of land utilized for agriculture by 88%. It's simple to understand how this may alter laws in several locations around the globe. Hunger is a major global problem that is exacerbated by conflict, unstable economies, and climate change. In 2023, 733 million people were estimated by the UN to be food insecure, a number that had sharply climbed in recent years. Furthermore, by removing lengthy supply lines and lowering the requirement for land, electro-agriculture has the potential to bring food production into urban areas. We think the method can be applied in areas where conventional farming is challenging. Once fertile terrain is becoming unsuitable for agriculture due to climate change, which might be a means of ensuring food production. But can it operate on a large scale? Is it only a novel approach to plant cultivation, or does it actually solve an issue? Solving the world's food crisis is too difficult and perhaps too inefficient financially. One major barrier is the requirement for energy. In 2023, it will require nearly 5 times as much power to create enough acetate to feed the whole U.S. population, according to studies. Without large investments, scaling up renewable energy would be difficult. Another problem is cost. Another high-tech agricultural technique that is still costly is vertical farming, which requires artificial lighting. Electro-agriculture solves that issue, but it also creates other ones. Vertical farming is inefficient because plants reject the majority of the light they get. We can significantly reduce light consumption and energy expenses using electro-agriculture. It's unclear, though, if these cuts will be sufficient to make the device useful outside of the lab. Plants 2.0 will be released soon. Despite the uncertainties, researchers remain optimistic. Electro-agriculture has the potential to completely transform the location and method of food production if it develops as expected. Large fields may eventually give way to reforested landscapes as urban farming becomes more common. Scientists are also employing genetic engineering to optimize plants for acetate-based growth, hoping to make staple crops like potatoes, rice, and wheat compatible with this innovative farming method. This technology has the potential to impact objects beyond Earth. Because electro-agriculture can function in complete darkness, it has the potential to completely transform space travel. Mars's thin atmosphere, which is 95% CO2, makes it the ideal planet for acetate production. If scientists can refine the technique, future astronauts may grow their own food in underground Martian homes. Even though the technology is still in its infancy, experts are hopeful. This is only the start. Over the next 2 years, we anticipate making significant progress. It's unknown if electro-agriculture will lead to a major shift in how people grow food, or if it will become a specialized technique of food production in urban areas. However, the idea of farming without sunlight is definitely no longer just science fiction.